Now we've taken a look at a Darlington pair amplifier and a preamp, and the reason I did that is I was looking at really a simplified version of what's inside our AM and FM radio. You can see here it's a lot more complicated looking, and the reason I made it simpler was to get a handle on what some of the voltage gains were going to be, and then we'll do some more calculations shortly. Here's our Darlington pair amplifier. First thing you notice here is there's some resistors stuck in here, and these are going to be explained in just a few more pages. Also, the main thing to notice here is this single-ended supply. You got a 9 volt battery powering this radio, and of course ground. What we're looking at before was a plus and minus 5 volt supply. This is really just going to shift it, having a difference around 10 volts, in this case 9 volts for the 9 volt battery. We're going to use some biasing to essentially lift up the positioning of our voltages to be halfway between the two supplies, like we were doing with the plus and minus 5 volt supply. Analyze this in just a second. This section over here is coming from the output of the radio, and we'll take a look at this in the next lab, is passing through a very large capacitor here, which for audio frequencies looks like a short circuit, but for DC is an open. And the same is true of this. And we basically have a voltage divider in here, and this is the volume control on the radio. And so it's allowing us to control what we finally hear in the speaker. So we're able to get quite a bit of voltage gain and current gain out of this stage, but we're able to control the input signal to get a reasonable sounding at our output. Now I've simulated this circuit to take a look at the actual results, but maybe we could take a look at seeing if we could figure out roughly what the biasing is of the circuit. It's a pretty complicated circuit, and so I want to show you a couple ideas or some tricks for looking at a fairly large schematic like this to figure out where are things biased at. Since the betas of the transistors are fairly large, that means their base currents are fairly small compared to their collector currents. But what I'm going to do in analyzing this is assume that all base currents are negligibly small. Then we can solve for collector currents and then come back and put in a finite value of beta and even check to see if that was a good assumption or not. Or we can run the SPICE simulation and see how close we come. Okay, so here again, here's our Darlington pair amplifier. Here is our preamp, an extra resistor stuck in here. And then really here's some biasing that's stuck in to lift up the voltages between half the supply, which would be around 4.5 volts or so. So I took the same schematic again, and I'm going to assume that roughly the drop across the diode is around 0.7, and that the base emitter drops will be somewhere around 0.7 unless we calculate them to be different. Where should we start? Well, that's always a tough question, but let's just try this. Kind of labeled where I kind of chip my way around here, but here I've got two transistors. Let's assume that they're basically identical, although one's an NPN and one's a PNP, and here's my 9 volt supply. Here's ground. Let's assume that the biasing is going to put us right smack in the center of this. So let's assume that this is about half the supply. We'll come back and check to see what that was reasonable later on as we calculate stuff. Again, there's only one solution to this thing. We'll run a SPICE simulation to see how close things come, but just using a little common sense and a little bit of approximation, we can kind of chip our way around the schematic. And the purpose of this is to show you that you can roughly get a handle as what's going on before you even take a measurement or do a simulation. If this is 4.5 volts here, I'd like to try to figure out the current that's biasing this loop here. So if I could find the voltage across this resistor, or at least estimate it, then I could figure out some of the currents coming down this path. Alright, this node voltage is 9, and let's assume that the drop across here is 0.7. You can see we're going to go back and refine that a little bit. If the current in here is the base current of Q13, and if this were again in milliamps, and this would be in microamps, and that's going to basically flow through this 100 ohm resistor. So if you had microamps flowing through a 100 ohm resistor, you'd have hundreds of microvolts. So roughly the drop across this base emitter plus this resistor is dominated by the base emitter drop. Let's assume this is 0.7. And so this node voltage then would be 0.7, and then this is sitting at, say, roughly half the supply. These were two identical transistors, basically dividing the voltage in half. So the current flowing in this resistor, because it's an open for the cap, would be 9 volts minus this node voltage, which would be the 0.7, really plus 0 plus 4.5. So we got about 1.2 milliamps of current in this resistor. most of that is going to flow here because let's again assume that all base currents are negligibly small. So most of that 1.2 milliamps would come here. And again, we've got another base current. Let's assume that that's negligible. So basically what's flowing in here is about 1.2 milliamps. So this is roughly biased at 1.2. Now we had, in our previous few pages, had estimated a biasing of 1 milliamp. And I did that purposely just to get an idea how much gain we get out of this one stage. And we did approximate that as around 127. So that's my step number 2, estimating that current. And then step number 3, estimating this current. And since the base current is negligible, most of that's going to come over here. And then we'll do a calculation shortly. The drop across here, let's assume it's about 0.7. And then the drop across this resistor, because we've got 1.2 milliamps flowing through it, would be that times the resistance. And that turns out to be about 0.4 volts. So the voltage across the diode and the resistor, which are actually between the two base leads of Q11 and Q12, is going to be 1.1 volts. If the drop across this resistor is negligibly small compared to 0.7, and likewise for this, that means that the 1.1 volts is divided across these two PN junctions. And so the voltage across here can't be 0.7, but typically half of the 1.1, so about 0.55. But I could go back and recalculate this, but it isn't going to change this by very much because these were so much larger than this. We started out with a guess, and then we could refine that guess if we want to, but we got some idea the current roughly flowing through here is about 1 milliamp or so. So that's step 6 and 7. Come back over here, step 8 was that if I have 1.2 milliamps, no DC will go in here, it'll all go in here. And so what I've got is 0.7 plus 1.2 milliamps times 47 ohms, which is about 56 millivolts. So this node voltage here is about 0.756. Now this node voltage here is about 4.5, and so the voltage across this resistor is 4.5 minus 0.756. So that's the current coming in to this resistor. None can go on the capacitor, it has to all go in the base. So the base current to be about 8 microamps. Because I missed a step here. These can be done, of course, in almost any order. I guess I skipped 10 and 11 over here. Let's just take a look over here. With the voltages across here being less than 0.7, that means these transistors are sort of at the edge of the active region, not fully in it. So that means that the current flowing in the collectors are very small, and that means that the collector current here is even smaller because, it was likewise, I should say, small because this is beta times this current. What I'm trying to say is that there's very little standby power in these transistors, very small currents, because with this bias that basically cut off, it's sort of putting these at, again, not totally in cutoff, but we're at the edge of the active region. Voltage around this loop has to be, again, 4.5 volts, but since no DC can flow this way, then you think of the impedance of the speaker as being approximately resistive, then the drop across it would be essentially 0, and all the voltage this node would be across this capacitor. So what this is doing is really biasing our transistor circuit at a point, and then we're able to block that DC and get the AC across the speaker. Okay, so we got a rough handle on some of the values of the biasing voltages and currents. So we're going to do an AC analysis. Since the preamp has about 1.2 milliamps in it, we should expect a gain of around a minus 127. So we'll take a look at piece-by-piece simulation of the circuit. I'll put a small enough input signal so I don't clip the output. And again, these models are available on 404 homepage under a piece-by-piece library for the course. Take a look at what we've got in terms of results here. Node voltage 4 is the voltage across the speaker, and you can see here that I've got about 1.4 volts peak to peak for the input that I have. And because we're biasing it kind of at the edge of the active region, then our crossover distortion is actually reduced because we don't need as much voltage now to turn on the transistors. This is called a Class AB operation. We did a strictly Class B in 302 and 303, and so this is one way to reduce distortion. Now if we look at node 12, which is actually the input to the preamp, the voltage across there you can see is a little bit distorted, although that distortion is somewhat eliminated by the time it gets to the output, although again there is some in here too. We can roughly get the ratio of the two. Again, you should do this when it's not distorted, but it's approximately the same as the linear case. We're starting to see the distortion pop up, but the ratio of those two, the output peak to peak to the input peak to peak, is about a gain of minus 98. So it's not exactly what we predicted. Let's see if we could also take one more peek at the voltage coming into the Darlington pair. This would be node voltage number 8. And the voltage there is actually 1.8506 peak to peak. We take the ratio of V8 to V12. This is the preamp gain. And then the ratio of V4 to V8 is actually the Darlington pair gain. Sure enough, gain's around a minus 127 that we had approximated before we got to look at the actual schematic of the radio. So that's coming up pretty close, and that's good. What's off is actually the gain of the power amplifier. It's not 1, but it's actually 0.778. And part of that's coming from those 100 ohm resistors being stuck in, and a few other things too.